A warm welcome. This is Control Systems course with lecture 2.3 focusing on static and dynamic error coefficient, steady state error and time response analysis. Normally, the error coefficients are of two types. One is static error constants and the other one is generalized error coefficients. While considering static error constants, these errors will be occurring where the position, the velocity and the acceleration of the system are subjected to error. So we can consider a system, a mechanical system or an electrical system where we can find out the position error, velocity error or acceleration error. In such a cases, those constants are represented as Kp, Kv and Ka value. Kp is the positional error constant whose equation is limit s tends to 0 g of s into h of s. While velocity error constants Kv is limit s tends to 0 s into g of s h of s, and acceleration error constant Ka is equal to limit s tends to 0 s square into g of s h of s. While considering the static error constants, generalized error coefficients are much more different. Generalized error coefficients, they directly mean the differential term of the stated function. Here we have generalized error coefficients as C0, C1 and C2, where C0 is equal to limit s tends to 0 f of s. It is a function of the system what we are going to represent. And C1 is the limit s tends to 0 d f of s by ds, and C2 is equal to limit s tends to 0 d square f of s by d square. And while considering C3, C4 etc., it goes on with the increasing value of the powers of the derivation term. Here f of s is nothing but it is the transfer function. It is the transfer function. It is not, it is a loop transfer function, which is the value is 1 by 1 plus g of s into h of s. Actually, how we represent is, we represent the open loop transfer function as g of s into h of s. Closed loop transfer function as g of s divided by 1 plus g of s into h of s. Hence, between the open loop and closed loop, we represent the transfer function as a loop transfer function, and its value is to be 1 by 1 plus g of s into h of s. And the correlation between, or the relationship between the static error constants and generalized error coefficients is very simple. C0 is equal to 1 by 1 plus Kp, C1 is equal to 1 by Kv, and C2 is equal to 1 by Kv. We can consider this E of s value as a substitution effect here. We have C of s is equal to G of s into R of s. So now when we take E of s outside, we get 1 plus G of s into H of s, which is equal to R of s. Therefore, E of s is equal to R of s divided by 1 plus G of s into H of s. Now we have calculated the error with respect to Laplace transform, and the steady state error is limit s tends to 0 s into E of s. And substituting, we'll get this. Now let us see the case of steady state error, that is when and all we'll be having the constant steady state error. If it is a type 0 system, type 1 system and type 2 system. What does this type means? Nothing but type 0 represents that there is no pole at the origin. Pole is nothing but the s value present at the denominator of the transfer function. If it is a type 0 system, there is no pole at the origin. If it is a type 1 system, there is one pole at the origin. And if it is a type 2 system, we will have two poles at the origin. Poles are nothing but the denominator roots. The roots of the denominator polynomial of the transfer function is known as the poles. Suppose here, when in steady state error condition, if it is a type 0 system, then we'll have a constant steady state error only when the input signal is a step signal. If it is a type 1 system, then we'll have a constant steady state error only when the input is ramp signal, and in type 2 system the input should be a purely parabolic signal. Only then we'll get the constant steady state error, and this constant steady state error is given by ESS is equal to 1 by 1 plus Kp for unit step input. For unit ramp input it's equal to 1 by Kv, and for unit parabolic input is equal to steady state error is equal to 1 by Ka. On substituting the values, here we have if it is a Kp value, here we have Kp value. If it is a type number, for 0 Kp is constant, otherwise it is infinity value. For Kv, I mean if it is a type 1 system it is constant, if it is a type 0 system the value is 0. Rest of the, for the higher number of type numbers it is infinite. Similarly for Ka, if it is a second, type 2 system, it is constant. Below that it is 0 and above that it is infinity. Similarly for input signal of Kp, Kv, Ka, the type number of the system, if it is 0, 1, 2, 3, let the value become 1 by 1 plus Kp, 1 by 1 Kv and 1 by Ea. Here it represents the steady state error. This is not Kp, Kv, Ka. This is the steady state error at that condition. So steady state error will be, in case of type 0 system, it is constant, for above it is 0. In case of positional error constant, if it is a velocity error constant, it is infinite for below type numbers. I mean below the type number 1 it is infinite, and above the type number 1 it is 0, and at the type number 1 it is 1 by Kv. Similarly in Ka condition, I mean the acceleration error constant, the steady state error is 1 by Ka for type 2 system, and the rest of the types, if it is type 0 or type 1 it is infinity, and above the type 2 system it is 0. And while considering the time response analysis, there are two different types of inputs which can be applied to a control system. One is the reference input, which we are providing it as an input. It is called command input. And the other one is the disturbance. The external disturbances are typically uncontrolled variations in the load on a control system. In systems which are controlling the mechanical motions, load disturbances may represent forces. In voltage regulating systems, variations in electrical load area may occurs as a major source of disturbances. So including all these, we have to find out the closed loop transfer function. Because in closed loop transfer function, we'll consider the feedback element, the error element, controller action, etc. So m of s is equal to b naught into s power m plus b1 into s power m minus 1, etc. till bm, divided by a naught into s power n plus a1 into s power n minus 1 plus a2 into s power n minus 2 till an. This will be the transfer function of the system representing for time response analysis. Thank you.